Alright, so let's start with a question for you. Rob is starting a new lesson, right? We're studying chapter 6 today. So my question to start is, does this book have energy? Does this book have energy? Yes, yes. Depends. Yes. I'm going to go with depends as the right answer, actually. Because there are times where this book won't technically have energy. So in this chapter, we're going to start talking about the concept of energy. But like right now, if I'm holding it, like Regina said, what does it have? Yeah, we talk about potential, and you guys have heard this in physical science so many times. This chapter is almost like the concept should be things that you've heard already, but the math is going to be stuff that's new, right? The math is what's difficult in an honors physics course in high school versus physical science in 8th grade, which teaches all these ideas, but not really the concepts. So this book definitely has energy at times. So Regina gave the example and she said it sometimes has potential energy. So why does it have potential energy sometimes and not all the time? We're going to obviously get into potential energy and the whole concept of it, but from your background or what you know, why does it sometimes have potential energy and not all the time? And not all the time. Jack, what do you think?
Because sometimes it has forces acting on it. Like right now it's in Earth, so gravity. Right now you're flipping it, so there's the force of your hands. But other times, like say it's just still in a space with no forces acting on it, it wouldn't have energy.
Okay, you're like on the right track, but if we're on the Earth, it's always got what kind of force acting on it?
Gravity.
Gravity. So it always has gravity acting on it. Now if we were in outer space and we were outside the gravitational pull of something else, then that'd be different. But on Earth, it always has the gravitational pull. But I can say this, like right now, it definitely has potential energy, right? Why does it definitely have potential energy right now? Not the normal force. Good idea, though. Not the normal force. Okay, how about this? There, technically doesn't have potential energy.
Because there's no fall off the table.
Because you could fall off the table? Okay, I like that. It has the potential to fall off, okay?
There's nowhere more down to go.
Yeah, there's no further way to go down. Now, obviously, that's for this room, right? I do this and whip it out the window, and suddenly it definitely has potential energy, right?
Break a
But
hole
what
in
if the
the
building
floor.
If the building collapses, it suddenly has potential energy.
To read
So
the
what is
code.
potential energy? What is potential energy a function of?
Space.
For itself, space. Give me a better explanation. What is it really a function of? Again, here it has some, here it doesn't. But again, if the floor broke, like we're saying, it would have potential then it starts falling. So what is it a function of? One word. One word. Close. He said distance.
Displacement.
Close. Awesome.
Area.
I like that connection.
Location.
Specifically, I mean a little bit more than that. It's getting closer each time. Location was the last answer that was closest. So this is a location, and then so is this. Those are two different locations. But in both those locations, it has the same potential energy. Height. There's the word. Very good. It is a function of height. So, relative to the ground here, this has potential energy. The noise it makes is the energy it's losing upon the collision to the earth, or the ground here. When I push it off the table, it gains another type of energy we're going to talk about today. What type of energy does it gain as it's falling toward the ground? What's the other main type? Kinetic energy. Right there, right? So we're going to talk about kinetic energy and the concept of motion with kinetic energy. We're going to talk about potential energy and height. We're also going to talk about what's called work. And in physics, work is different than like your homework. Okay? The scientific definition of work. And the scientific definition of work is that you apply a force to something over a given distance. So I'm currently doing work on the textbook. Use the word on, by the way. I'm doing work on the textbook by pushing it across the table here. Now, if I were to simply, I don't know, hold the textbook stationary here, I'm not doing work. But yet when I'm pushing it along the surface, I am doing work. If I were to try to push it along this surface and it won't budge, I'm not doing work. So what does work require? Again, not doing work by pushing it, not doing work by holding it, but when it's moving, I am doing work. So what does work require for it to make sense?
Friction.
Okay, friction. Doesn't have to be friction. Friction is one type of work that can be done.
I was going to say kinetic friction.
Not kinetic friction, but again, friction is a type of work that can be done.
Displacement.
Displacement. Yeah. case, we're going to use the phrase distance actually, but it involves motion. In order for work to be done, motion has to occur. If things are not moving, work cannot be done. So, as strong as you may think you are, if you're a bodybuilder or if you're lifting weights, holding a dumbbell or a barbell over your head, holding it there, you're not doing any work because you're holding it there. The minute you start to lower it, then you're doing work. You're doing work against gravity by lowering it down to the ground. The same concept applies for if you were, let's see, holding a bow and arrow, right? You pull back on the bow and arrow and you hold it right here. While pulling back, you're applying a force over a given distance. But when you hold it like this, although it does take force, like obviously you guys know this if you've shot a bow and arrow, to hold it where there's tension in the cable, it's not like you're not applying a force, you have to be applying a force. But right now, no work is being done at all because I'm not moving as a result of the force being applied. While I pull back on the bow and arrow, work is being done. But while holding it in that stretched position, I'm not actually doing any work.
So like, if you have like a boot on your car and you start like moving the engine, and it doesn't move, but then you like break the boot, like that's when you start working and like not when you were.
Sure. You know with the boots that like lock your car and stuff?
Yeah, like when you get like the ticket.
Yeah.
Yeah.
You drive? You know boots and cars already? You guys all.
But a driver.
She's already got a few.
Okay. I was gonna say, yeah, I got a boot in your car.
No.
But yeah, that's a great explanation. That's a great example. If you try to drive with the boot that locks up the wheel if you don't pay your tickets, you're not going to move, right? You can hit the gas all you want, and it prevents rotation of your axis. Now, what will happen over time, you put enough force, you'll probably do some damage. You'll probably put too much torque on the axle, and you might even like snap the shaft of your axle. But over time, if you do eventually break the force that's holding it from the boot, the car may start to move, and then you are doing work on the car.
Yeah, illegal work, but work
Illegal
like
work, sure.
That's a legal pin.
So work done, again, is a function of motion. It has to be moving for work to be done. So again, when you drop something, it has energy because it's at a certain height. But then I went into the concept that I said, when it's here, it has no energy. So what matters in a lot of these problems is what we're going to call the ground. So for example, if I call Park Avenue the ground, then this textbook has potential energy, whether it's here, whether it's on the ground in the classroom, whether it's on the radiator, whether I bring it down to room 202, it still has potential energy if I'm calling Park Avenue ground level. But if I call the ground of this classroom ground level, then this book only has potential energy when it's above the ground of this classroom. So right now it has potential energy, but right there, it has no potential energy because it's sitting on ground level. Isabella, what's the current height of this textbook relative to the floor? It's 0. And Isabella told us that it's a function of height. Okay, it's a function of height. So when there is no height to the object, meaning above what we're calling the ground, it has no potential energy. And I like what Regina said before. It's like the potential to do something. The potential to do something. So when you have potential energy, the book or the object has potential to move, to gain velocity, falls. Maybe even we're going to talk about springs and slingshots a little bit with rubber bands and that idea. It has the potential to move because you're storing energy in the spring. Have you ever used a slingshot before? Or a bow and arrow? A bow and arrow is a perfect example. You're storing energy when you apply force to it. Because when you release, what happens? All that energy comes outward. And you guys did this last chapter when you made those catapults, or last quarter. Right? A lot of you, without realizing it, you were using potential energy. And we're going to see potential energy in this chapter and how that plays a role with springs, which are really, really important. We're going to spend a good amount of time on the concept of what a spring is and how everything can be modeled as a spring. Everything, literally, can be modeled as a spring.
Energy only takes like height to count. Does that mean that this will take like horizontal movement?
It does, and the horizontal movement, because of its velocity in matter. And if there's friction that is resisting the horizontal motion, that's also energy. We were talking specifically about potential energy in that
Oh,
circumstance.
okay. So then like if like the car with the blue one, that one has no energy because it's not moving.
When it wasn't moving.
Yeah.
As soon as it starts moving, it has kinetic energy. If you slam on the brakes and the car skids to a stop, it technically loses energy to friction. And we're going to talk about negative work because friction is what loses energy in the system or causes your energy level to decrease. And think about that logically, right? Think about swimming in a pool. When you swim in a pool, sure, it helps you with buoyancy to stay afloat, but try to walk across that same pool in the shallow end. It doesn't work very well, right? You feel this viscous, resistive force against your body. And this is a great workout for anyone that's into sports, take like a baseball bat or a lacrosse stick and swing it underwater. You feel this resistive force. That force is a function of your velocity. So the harder you swing, the harder it pushes back against you. That's why there's a lot of underwater training that happens with professional athletes. They train in bodies of water for that reason. So what I'm getting at is that friction can do negative work, lowering your energy. If I took a normal baseball bat and swung it, and then take that same baseball bat and try to swing it underwater, it's going to go a lot slower. Because the energy that you're putting into the bat is getting dissipated, used up by the friction between the fluid, water, and the bat itself. So we're going to see a lot this chapter about transformation of energy. Not just what is energy, but how does it change from one state to another. And you talked about this in chemistry last year, whether you realize it or not. Q equals mc delta T. That was energy of thermal energy. Specifically having to do with the temperature of a substance and how much energy it has or needs to change its temperature or its phase. Right? Remember, change it from a liquid to a solid or a solid to a liquid. That was called, you better remember your terms, whatever, it doesn't matter. That was called fusion, right? And then the other one, right? Or solidification, you could say, or melting if you want to use that phrase. The technical phrase is fusion there. But the idea is that if you gain or lose energy, it changes something about the problem. In chemistry you saw it, and now we're going to see it a bit more in physics. These are our objectives, kind of what I was just going through there for the first section. We're not going to get into potential energy until 6-4, which is going to be in our next class. So today's going to be about work and then about kinetic energy. So let's take a look at this definition. Scarlett, can you read it for us? Just read the definition right off. So if we think about this, again, it's along the direction of displacement, along the direction. So if I'm moving left to right and my force is pushing me left to right, it means it's in the direction of displacement. But if I'm holding something like this and I'm pushing up on it, and yet I'm moving left to right, the force I'm applying is up to hold it, my motion is left to right. So that force would not be along the direction of motion. Again, if I'm moving this way, this is motion, but the force I have to apply to this to hold it up is an upward force. So those two things are at a 90-degree angle, they're perpendicular to each other. So that circumstance is a little bit different. We are specifically concerned about, again, the force applied in the direction of motion. So what do I mean by this? Let's take a look. If I've got an object, and let's say it's being pulled by that force. Let's say it's sitting on a frictionless surface. We don't have to worry about friction at all right now, but it's being pulled by this force, F, and that's at some angle, theta. If it's being pulled by this force F at an angle theta, well, what does that mean? It means that really it's being pulled to the right and up. Jack Morrow, can you guys open the windows in the back? Thanks, guys. So we've got pulling up and pulling to the right. Pulling up and pulling to the right. So in this circumstance, what we're going to notice is that part of this applied force is in the direction of motion. Because if I think about this object resting on a surface like this, and I'm pulling on it, this is back to the example of like a sled, where you're pulling on a sled and your younger sibling is sitting on the sled and you're pulling them across the snow. A frictionless surface with an applied force F. Sure, if you pull hard enough, maybe the sled will come off the ground a little bit. That's if Fy, this force, were to exceed the gravitational pull downward. Remember, gravity is always acting on all objects here. So when I look at this object, what I recognize is that the applied force is at an angle and motion is only in one direction. What direction is motion? It's horizontal here. So what part of the force do I even care about? All I care about is Fx in this problem. Fy pulls upward. Upward is not the direction of motion in this problem. Motion is left to right. So this force component, Fx, what do we usually call this when we find the x component? It's F cosine theta. Look at your formula, guys, look at the top. Fd cosine theta. So another way to write this formula, and your book writes it this way, is by writing F parallel times D. And F parallel means the force parallel to motion, which is F cosine theta. So we could write this as F cosine theta times D. So this formula, I write it as F d cosine theta. You're going to see it that way on your formula sheet. You'll see it that way in the textbook. But if you want to start by writing F cosine theta times D, so you remember that what are you really using? You're using a component of the force. Simply a component of the force along the direction of motion. So what is that angle theta? That angle theta is the angle between the force and the direction of motion. This was motion, my hand, and that's the force. So there's the angle theta. What if instead, ready? What if instead I had a scenario like this? What if I had, this was a traditional way of getting fossil fuels for a long time. Horses were strapped in, and there was a pulley system. So here's your horse right here, and there was a cable attached to the horse. There was a pulley system, and then that pulley ran over a mine shaft, which went down toward the ground. And in the mine shaft, they had coal and other fossil fuels they would excavate from the earth and lift them up to the surface, and then coal was burned in the fire. So here's the horse pulling over a pulley into a mine shaft. I'll try to draw the mine shaft so you can see that as well. Okay, that's the mine shaft opening right there. And this pulley system was set up in such a way that the horse would apply force to the right. Yet, this object would move up and down. This object would move up and down. So, what's interesting to note is that there's tension in the cable. If I were to identify and look at this body here at the bottom, I've got tension pulling up, and I've got gravity pulling down. I'm drawing tension significantly longer because it's going to move upward. Tension overcomes gravity. And in this problem, if we look at it, I could say that tension acts up, motion is up, so the angle between these two values is going to be 0. Again, it's moving upward, and the tension is upward. So how do you find the angle between two vectors that are in the exact same direction? It's always 0. If I'm moving to the right and my force is to the right, the angle between them is 0. There is no angle. So in this kind of a problem now we have to consider that it's moving upward. But what about the horse? Right? The horse's force is this way. I'm going to call this Ft, the force of trotting, when the horse trots. Oh no, T for tension, don't it? Let's call it Fp. We'll say pull for now. So the horse pulls to the right. The horse pulls to the right, yet this object moves up. So the horse, by definition of work, is not doing any work on this object at all. Because if I move to the right, and then the thing I'm pulling is moving up, what's the angle between to the right and up? What's that angle? Everybody. 90 degrees, right? Between to the right and up. What's the cosine of 90? Come on, guys. It's 0. It is 0. So a lot of you said 0, but a lot of you said 1. Cosine of 0 is 1. This is basic trig that you learned last year, and you've been recurring or learning again this year in your pre-calc honors course. You got to know these angles. The cosine of 90 is indeed 0. So if I'm pulling this way, which the horse is doing, yet motion is upward, that angle of 90 degrees makes this cosine of 90 become 0, which means that the horse is not actually doing any work on this object here. The horse is doing work against the tension in the rope. The horse is doing work against the tension felt in this rope, Ft right there. That's what it's doing. Now, we could also have scenarios, and you could have a scenario like this very easily, where an object is being pulled upward at an angle. Let me scroll down a little bit. Or zoom out a little bit, rather. An object is pulling upward at an angle like that. Let's put the object here. Gravity pulls down on it. And yet maybe this object is moving vertically upward. So motion is in green in this scenario, and the applied forces are in red. That force, F, is at an angle to the vertical. Let's call that angle theta right there. So if I want to find the work done by that force, it's still FD cosine theta. Because again, theta is the angle between motion and the force. For this topic, for this concept of work, whenever we talk about theta in the formula, we're talking about the angle between the direction of motion and the applied force, not the angle between the force and the horizontal, like we kept saying in the past. We kept using theta as the angle between the force and the horizontal. It was always theta. And then we got to inclined planes and realized theta could change. Well, here's another example where with work, we're going to be looking at the angle between the force and the direction of motion, which is shown in green here. This is like an elevator. An elevator cable pulls you upward, but technically there's slight pitch to that cable. There's slight pitch to that cable. And then that cable goes over a pulley, and then that pulley comes back down to what's called a counterweight, which stabilizes the elevator. So there's a slight angle. Even if that angle theta, right here, maybe it's 1 degree, 2 degrees, 3 degrees, whatever it may be, there is a slight angle there. So we could pull on objects that move them horizontally like this. We could pull on objects that move them vertically like this. Then we could have this scenario, right, where we pull horizontally and then the object moves vertically. So there's different ways to interpret what we're seeing based on the question. But the key, again, is to be able to model this to any problem. The concept of work being applied to any given scenario. Whether that given scenario is on your homework, on your problem set, on your test, whether it's a new scenario on your homework you hadn't seen before, you want to be able to expand on this concept and apply it to that. The new other thing that we're going to see here is that Newton times a meter, my units for force is Newton, my units for distance is meter. That's defined as what's called a joule. Joule, joule. Capital J for the unit itself. This is the unit of energy that we're going to use. This is the unit of energy. Anybody know what unit of energy we use in the English system? This isn't the metric system, by the way. We've been using metric all year. Anyone know the English unit of measurement? It's not watts. That's power. We're going to get to that in section 610. And watts are actually a metric system unit, not English. Although we still use it in American blocks all the time. Joules is the metric system. Calorie is one of them. Very good.
Is it Coulomb or?
Coulomb is electrical charge. Good idea, though. Calorie is one of them, and you see it on your food packages, right? What you see, by the way, like 100 calories, those are actually kilocalories, they're not calories. That's why it's capital C. It's 1,000 actual little calories. That's a whole other side point. What's the other unit, though? Yeah, lowercase k, capital C, kilocalorie, which is capital C calorie for us. There's another unit called BTUs. They're called British Thermal Units. BTUs. Just like we have inches instead of centimeters in the English system, BTUs are used a lot for the amount of energy. British Thermal Units. Okay, and then again, as Vinny said, calories. And we use calories in the in our American system, I'm going to say, which is really, the American system is all messed up. You know that, right? It's a combination of like the English system and then some metric stuff where we feel like the metric's important, but then we go back to English for other things. So it should be one or the other, and it's not, unfortunately. All right, let's take a look at an example. If 840 joules of work are done in the process of pulling on a shopping cart with, the shopping cart 12 meters with a force of 75 newtons, determine the angle the arm makes with the direction of motion. So we need to think about this, right? I hope you've grocery shopped before at some point in time. If you haven't, get yourself out there in the world and grocery shop, okay? If I'm pulling on a grocery cart, this is what it looks like. I'm not pushing on it, I'm pulling on it. I can push on it, and when I push on it, I'm technically pushing down, right? When you walk around the grocery store, you push. But when your parents are, bringing you as a kid, they'll have you sit in that little area, right? And then sometimes they'll just pull on the front of the grocery cart. So I'm pulling on the grocery cart right now, and this is literally the scenario we have. So my question is, what is the angle between the Apple Pencil and my arm? That's the question, really. I'm going to go through it again, as I pull. Okay, as I pull on this. So the question is to find theta. So if we look at this problem, we can see we know the amount of work done, we know the distance traveled, we know the force applied, so this becomes a plug and chug. And I say plug and chug because there's really not multiple equations to use. There's not substitution method needed. There's no like sum of the force in the x, sum of the force in the y, put them together. All that stuff doesn't have to happen here because it's only one scenario with only one formula. Let's start by listing our givens. The work done is 840 joules. The distance you pull on the grocery cart is 12 meters. Notice I'm going to use D for distance in this section. I'm not using X. X for displacement. I'm using D for distance. And the force applied is 75 newtons. And the question says, determine the angle between that force and the direction of motion. So for a lot of these problems, we're going to notice that we don't really need a free body diagram anymore. Some of them I'm going to talk about when you want a free body diagram. Here I'm going to draw it so you can see it. Is it necessary for the problem? No, it's definitely not necessary. That's the force. That's gravity. There may be some friction force. There definitely is friction force, really, in real life. And we know that the direction of motion is shown there. I like to designate motion with a dotted line. I really do, because a solid line indicates a force. And still, some of you are putting solid lines when you should have dotted lines. Like on the last test, right? When you have a force, if you break it into components, you can't show the force and the components, because then you have extra forces there. So if you're going to break it into components and still have a force applied at an angle, you should probably use dotted lines for those components. Or remove the original force and only show the components. Or draw two separate free body diagrams, one like this, and then one with the components of the force in the next one. But again, a solid line on a free body diagram is indicative of a force. A solid ray. Arrow, ray from geometry. A solid arrow coming from the mass on a free body diagram indicates a force. So I'm using a dotted line to indicate motion. Now, this problem asks us to figure out that angle theta. So we know our formula for work is going to be F times D times the cosine of theta. I'm looking for theta. How can we algebraically solve for theta? What would that become algebraically solving this equation for theta? What do you got, George?
The cos inverse of W over FD.
Good. Take the W, divide it by the FD. That'll equal cosine theta. And then do the cosine inverse. About 21 degrees. Should be around 21 degrees. If you didn't get that, there's a good chance you're in radian mode right now. Okay? Make sure your calculator mode says degree. Again, if you didn't get that as your answer. If you got that answer, you're good to go. And if you got something else that's not 21, there's a chance that you're either in radian mode or you forgot what? Come on, what else? There's a very common mistake in this problem. Who can figure it out? That part I didn't think of yet. If you forgot the cosine inverse or just did cosine, that could be a common mistake. But something else, algebraically.
You need to multiply the f times d before you divide by w.
Or, you're right. Good. Or put parentheses around your denominator. If you do 840 divided by 75 times 12, and you just type that in directly, it's going to do 840. It's going to divide that by 75, get an answer, and then it's going to multiply that answer by 12, which is not right, because you should be dividing by 12. So FD has to have parentheses around it. FD in your calculator has to have parentheses around it. Or, as Regina said, multiply FD to start. Okay, but if you're putting in the calculator, make sure you have your parentheses around FD right here. Okay? All right. Let's move. Next question. What would the angle theta be if the force is a horizontal force in the direction of displacement? And what about if it's in the opposite direction of displacement? So let's take a look at what we're talking about here. So here, let's take a look at the first scenario. Here's an object. We've got a force that is a horizontal force in the direction of displacement. So let's call displacement to the right. and we've got a force in the direction of that. And then scenario 2, in the opposite direction of displacement. So again, that's called displacement to the right. And in scenario 2, the force is opposite the direction of displacement. These are our 2 scenarios that we're asked about. What are the angles between the force and the direction of motion in both of these scenarios? What are the angles? Christina?
0.
Which one? On the left or right? On the left. Good. How come not on the right, Christina? The right angle is 180. Not right angle. The angle on the right is 180. Think about that logically, right? This is the angle between the force and the direction of motion. It's 180 degrees. But the other one had an angle of 0 because literally that's a 0 degree angle. Here's my motion, here's my force. It's 0 degrees. I point upward. If motion is upward and the force is upward, the angle is 0 degrees. If the force is ever in the direction of motion, the angle is 0 degrees. The angle is 0 degrees. Why is 180 important? Why is 180 important? Only moral? Come on. Look at the formula, look at the formula, look at the formula. Moral Vin, Valentina. Jack, Moral Vin, Valentina. And George. Right? Same hands I'm always seeing. That's why I'm asking for others. Why is 180 important? Look at the formula. I'm giving you hints. Look at the formula. Go back to the last slide. Back to the last slide. Look at the formula. Where would the 180 play a role? Use deductive reasoning. Where would it play a role? Is it the force? No. It's not the distance. So how does it play a role? What does it become? How does it change this problem? What happens here? What happens here? It becomes the theta. Agreed. Very good. And what is the cosine of 180? -1. It's -1. So what does that mean? Cosine of 0 is +1, but the cosine of 180 is -1. So what does it mean, George?
It's going in the opposite direction.
So what does that actually mean then, George? The work done is negative. What kind of a force acts in the opposite direction of motion? What is it? It is friction. Very good, Jack. Friction always opposes sliding friction. We'll talk about rolling friction next year. Sliding friction always opposes motion. So if I'm moving to the right and I'm sliding in the eraser, okay, sliding to the right, and friction acts backward to the left, that is the scenario on the right. So friction does negative work on an object. Friction does negative work on an object. If you want to be specific, we can say sliding friction to be really specific, because rolling friction is different. Okay, sliding friction does negative work on an object. And you can say because the angle is 180, and the cosine of 180 is -1. Okay. Now, technically speaking, I could do negative work on an object even if I'm not friction. Even if I'm not friction. There's a really crazy video, and it's not, I don't know if it's real or not. It's a video of like a baby running in the park, and like a falcon or an eagle coming by to try to like snatch the baby up from the ground. Has anyone seen this? Have you ever seen these videos of like bald eagles picking up like squirrels or picking up cats or dogs and flying away with them? People have literally lost their like pets to like bald eagles and stuff in Central Park and stuff. So this is video, and there's this baby, and the baby is like, I don't know, running or moving, and this eagle comes swooping down to pick up the baby. And the dad is like chasing after. I think it's video actually. I don't think it's actually a real video. Anyway, the point is this. The eagle grabs hold of the bird, whatever it is, grabs hold of the baby, starts flying this way with the baby on the ground, like just above the ground. The dad is running after and pulls the baby out of the clutches of the bird. Motion was that way, right? Motion was that way from the bird. Which way did dad pull? This way. So you don't have to be friction to do negative work. All you have to do is apply a force that opposes motion. So, for example, if you've ever seen those, the stunt devils with like, not stunt devils, stunt dummies, or dummies, whatever they're called, the test dummies in the cars, where they run cars into a wall to test out the airbags in a car. You know what I'm talking about right now?
Yeah.
Like, don't drink and drive. This will happen. You can see those commercials all the time. So the car drives. The car hits the wall. Which way does the wall push? Which way does the wall push? Which way is motion, though? So what kind of work does the wall do? Negative work. So when the applied force acts opposite motion, you're doing negative work. You're doing negative work. We see that on the next slide summarized nicely for us. Okay? The left side, these are both examples of negative work. There's a little toy car. Anybody have these, by the way? These little cars you wear with a spring? Where you can like pull back on the wheels and it stores energy. If anybody has like a lot of them, can you bring a couple into class? We're going to use them soon. If anyone else, if you have them at home, you still know where they are, the ones that they load energy into the spring, if you could bring a couple into class for the next week, I would really appreciate it. If you have like 100 of them, and you can donate like 10 of them, that'd be great also. I could buy them, I guess, but I just, anyway. So, motion is to the right, the force applied is to the left and down. Here, the force applied is to the left and up. The up and down don't matter, because motion isn't up and down. So the fact that this person's hand is pushing and pulling at angles, the up and down component, the y component of these forces don't matter. Because it's not moving. This car is not moving up or down. It's only moving to the right in all four scenarios. So when the force helps motion and pushes with the direction of motion, you've got your positive work on the right side here. But when the force opposes motion, you've got negative work on the left side there. Okay? So let's look at an example of this. So this is a more in-depth example of work. A more in-depth example of work. So we have a student pushing on a desk. The desk is given as 20 newtons with a horizontal force of 12 newtons, that's the push, a distance of 24 meters. Assume the coefficient of kinetic friction between the desk and the floor is 0.2. So we're going to do three parts of this problem. We're going to start by asking how much work is done by the student on the desk. Then we're going to say how much work is done by friction or the floor on the desk. And then we're going to ask ourselves, what is the net work? What does net mean again? Net means combined, or another word? Total or overall. I like overall because it makes me remember that there may be positive and there may be negative. So overall, there could be some balancing occurring here. So the question again is, what or how much work is the student doing on the desk? So let's start this problem. Let's draw the desk first. We know that there's a force applied. It's a horizontal force that the student is applying. The weight of the desk is given in the problem. What's the weight of the desk? It's given in the problem. What is the weight of the desk? 20 newtons. Why is that not the mass? I thought that was the mass, right? We always talk about the mass.
Because the weight is mass times gravity.
And what would the units be if it were mass, Christina? Kilograms. If it was a 20 kilogram desk, then I'm given the mass. But when I'm told it's a 20 newton desk, this is the weight of the desk. And then we've got the friction force pushing back, which I don't know what it is. I'm going to put FF in it. I also have the normal force. I should draw that, right? I do also have the normal force. This is that lab we did all over again. Except now, the applied force may not be balanced by friction. If you remember, we did the friction lab. You pulled on the carts, and you pulled on the carts so that it moved with a constant motion, so that the pull balanced friction. So you could say FP to the right equals FF pulling back to the left. That may not be the case here. We have to figure it out. If friction turns out to equal 12 newtons, then it will be the case. If friction is 12 newtons, then 12 newtons and 12 newtons mean we're in balance, right? It's either not moving or it's moving with a constant velocity, if that's the case. But we don't know what friction is right now. Meaning we don't know the value. But we do know what friction is. What is the formula to calculate friction? What is that formula? What is that formula? Justin? Yeah. FF equals mu k times Fn. And as Justin already substituted, he said, you know what? For these problems, Fn is mg. Be careful with that, by the way, because if it was a force at an angle, it's no longer mg, right? So Fn, where do we get Fn from? The vertical direction. In the vertical direction, this desk is not moving. So what are we in a state of vertically? A state of equilibrium. If we're in a vertical state of equilibrium, it means that we know that Fn is the same as Fg. So I replace Fn with Fg. Again, because we're in a vertical state of equilibrium, we've got this equation. If you need me to write it, I'll write it. That's the equation in the top right there. That's the vertical equation of equilibrium. Fn minus Fg equals 0. So Fn must be equal to Fg for it to equal 0. So we replace Fn with Fg. In this problem, we know what mu k is. Mu k is given as 0.2, and 0.2 times 20 is equivalent to 4. So my force of friction, turns out, is equal to 4 newtons. Okay, equal to 4 newtons. Alright, so we've got our force of friction, we've got our applied force. What will happen to this object with certainty? I want an answer and I want correct vocabulary used in the answer. Correct vocabulary. Jack.
It will move
Continue.
because the force of push is higher than the force of push.
Good. So it will move, but I can move if the forces are equal also, Jack. If the forces are balanced, I can be moving with a constant velocity, right?
Yes.
So what else do you have to add on to the end of your explanation? It will move with
Acceleration.
acceleration. Very good. The object will move with some acceleration. It has to. If there's an imbalance of force, force is the cause of acceleration. So this object has to accelerate in which direction? In which direction? Good. To the right. This, right? This outweighs this. So it's got to move to the right. So this object will definitely accelerate to the right. It will definitely accelerate to the right. So before we even get to part A, part B, and part C, are you going to be doing more work, or is friction going to be doing more work? Use common sense. You would hope you are, right? You would hope. If friction did more work than you did, it would slow it down. It would stop it. It would be like I'm pulling on, I'm pulling on, I'm pulling on, and let go. And as soon as I let go, it coasts until it stops, right? That's when friction is doing work, and only friction, so it loses energy, or it does negative work because of the friction. So this is going to do positive work, this is going to do negative work. We're going to calculate this for part A, this for part B, and then part C we're going to look and say, how do we see the overall amount? So let's take a look at the math for part A. So for part A, the math involved tells us work done equals FD cos theta, which is going to be 12 newtons, times the distance, which was given in the beginning of the problem. If you look back up, 24 meters, and it's the cosine of 0 degrees, which is really just 12 times 24, 288 joules of work. Again, that's the work done by the student, We then go to look at the work done by friction. Notice what I'm doing. I'm replacing F with FF. With FF to indicate that it is friction that I'm concerned with here. I could also use theta 1 and theta 2 maybe, so I can identify that those are different angles. Okay, theta 1 was the angle between the applied force in motion, which is 0 degrees. But theta 2, what's theta 2's angle going to be? What's it going to be? 180. We just went over this, right? Motion is that way. Friction is that way. There's the angle, 180 degrees. So for the second part of this problem, when we go ahead and look at the work done by friction, it's a force of 4 newtons, a distance of 24 meters. The distance hasn't changed, right? The distance doesn't change, think logically, but the force does because it's a different force. and the angle changes to 180. 24 times 4 is 96. Cosine of 180 is -1, -96 joules. -96. Isabella?
So why isn't, when you're substituting in for F, why isn't it like F minus F friction? Because isn't it all in the X direction?
That's a very good question, Isabella. In part C, we're going to address that. So if you wait like 30 seconds, we're going to get right to that. Great question. She's asking, why didn't we find the net force to start? Why didn't we say, you know what, 12 minus 4 is just 8? We could do that, actually, is the answer. But let's get to it in a moment. So in part C, it says to find the net work done. So we've got positive work done by the actual student. Which is 288 joules. And then we've got negative work done by friction. The work done by the student is 288. The work done by friction is -96. So the overall work done is what we're actually focused on for this problem. Okay, the overall work done. That'll be 192. That'll be 192. Now this is not the only way you could answer part C. What we can do is take Isabella's suggestion and look at part C. So for part C, what we can also do is this. If I want to find the overall work or the net work, and again, we're going to get the same answer. I'm just showing it again. If I want to find the net work, I could look at the net force times D times the cosine of theta. And that's what Isabella was talking about. She was saying, how come we don't balance the applied force of 12 with the 4 newtons of friction? So net force is your applied force minus friction is what it is. So this formula becomes F minus FF times D times the cosine of theta. Which means it becomes 12 minus 4 as my forces times the distance of 24 meters. What would theta be though here? If I'm looking at the net force, what would theta be for the net force? Yeah.
180 still?
Not 180. Think about which way it wins. It's a tug of war.
Oh, so I don't know, like 90?
Not 90. You're on the right track now. I'm pulling this way, right? Friction is pushing back that way. What's the answer?
0.
0. Because again, the direction of motion is to the right. The overall force would be to the right. So you could use this method that Isabella recommended and use cosine of 0 there, and you'll get 192. Now, why would I probably not use that method for this problem? Let's go to problem solving. This is where some of you really struggle on tests. I would absolutely not apply this method for this problem. Maybe another problem I would use this idea. Why would I not use it for this problem? Why is it more logical to use this as a solution method, Jack?
It's like just way easier. It's like adding two things rather than like multiplying.
Yeah, but there's more to it, Jack. Come on, think harder than that. You're better than that. Think harder than that. Then what do you think? You found the work in part A and B, didn't you?
Yeah.
In part A and part B, you found the work separately. If you didn't have part A and B, though, then either method is valid. So the preface by saying, you found the work done by each thing in part A and B. So why do this whole other method when you could just sum these together? You can't sum these together if you didn't have part A and B. So without part A and B, you wouldn't really have a better choice. Either way would work. I know you would, Jack. I'm just saying you want to be specific in the way you say it. So either of these methods is more than valid without parts A or B. But because we did parts A and B, it doesn't make sense to use this method. Although it is valid, we would want to use this method because it's so much easier. But if you're not finding the work for each thing separately, then you could probably do it all together in one step like we did down here at the bottom. Okay? So without parts A and B, I would take the second approach, which is this guy down here. Without parts A and B for this problem. This is why on the test sometimes I ask you for more than one thing on those for response. It'll say like, determine the force of tension, and then determine the velocity. There's a good chance that by getting the force of tension first, you'll then use that answer to find the velocity. And you'll see that on a lot of exams for math and science going forward, that part A affects part B, which affects part C, etc., etc. Okay, so think about the problem solving, not just how to get the answer, but what's the most efficient way to get to the answer. Okay, the most efficient way. It's a force, whoops. All right, let's take a look at example 4. We already talked about this, so this could be a real quick one. A person walks to the right while holding a mass of 10 kilograms at chest level. So I'm holding like a dumbbell, maybe it's 10 kilograms, or I'm doing like one of those kettlebells, kettlebell lifts like this. Imagine you're holding the kettlebell, and you're doing like a kettlebell walk, okay, like this the entire time, holding the kettlebell out in front of you. How much work does the person do on the mass? How much work does the person do on the mass? How do you hold the mass up? Which way do you have to apply a force to hold the mass suspended in the air?
Upward.
You have to apply an upward force to balance what? Gravity downward. So the applied force is upward. What's the direction of motion? If we're walking, unless you're walking on the wall, which you're not going to get either left or right, so what's the direction of motion? Horizontal. The applied force is up. The direction of motion is horizontal. What's the angle? 90 degrees, not 45, 90. The angle is 90 degrees between horizontal and vertical. What's the cosine of 90? Again, what's the cosine of 90? Zero. So how much work are you doing? You're doing no work. You're doing 0 joules worth of work on this object. Okay? Again, that comes from the fact that the applied force and the direction of motion, applied force. I know gravity pulls down, that's balancing it. But again, the work done equals F times D times the cosine of theta. And theta is 90 degrees. And that becomes 0. So the work done is 0. Again, I don't care what F actually is. I don't even need to do the work. So if I don't need to do the work. So if I'm taking a test and this is a multiple choice, this is another little bit of a hint. I've been really pushing myself to read your multiple choice work because I'm noticing that some of you ace the multiple choice and then others really struggle with multiple choice. And those that struggle with multiple choice, I've noticed that a lot of you do work that is not necessary. So for example here, could I figure out what the applied force is upward? Sure I could. I could say, well, how much force do I have to apply upward? What's gravity pulling down? The mass is 10. 10 times 9.8 means that the weight of the object is 98. So the applied force upward is 98. So this is really 98 times 8 times the cosine of 90. But why am I doing all the extra work to find out that F is 98 if I'm going to multiply it by 0 anyway? You follow what I'm getting at here? So you need to take the most direct route to answer questions. Some of you are taking these roundabout, ridiculous ways to get to an answer that actually ends up causing probably more harm than help. Because by taking a route that is not efficient, you have a higher probability of making mistakes along the way. By not including any of this other stuff, I'm not A, sidetracking my mind, and B, wasting time. 1 minute on the test means, you know what? Maybe you could have finished that free response that you didn't finish. Or maybe you could have gone back and checked your work later on instead of that 1 minute. So we need to make sure that we are taking the most optimal route. This is an example of exactly that. Do not need to do all of this. The answer is 0 right off the bat. The force is up, the motion is to the right, the angle is 90, no work is done because cosine of 90 is definitely 0. Okay, so think about this stuff when you're on tests, when you have a problem and you're like, man, this seems complicated. Seems too complicated for a multiple choice. Maybe there's a simple explanation that yields one of those 4 choices a lot easier than the complicated route you took. There are some people that didn't make up the test yet. I know you guys have to make it up still, so I'm not going to talk. But there's definitely a multiple choice problem that I could think of that involved exactly this idea where I would say 10 of the 20 or 18 that took it so far took all this work to get an answer that you could have gotten from just reading the problem. I'm trying not to give too much away because they didn't take it. But you don't always have to do all the work to get the right answer is what I'm saying. use your context clues, like in this case, to help. All right, kinetic energy, the second part to this lesson, and now we're going to finish in a minute, but I want to make sure to talk and to begin this. Kinetic energy is the energy associated with motion. The energy associated with motion. So that textbook I have before, I asked the question, does the textbook have energy? That was the question I asked. And a lot of you said yes, maybe, no, sometimes, depends. Well, it only has kinetic energy if it's in motion. So this eraser right now, it has potential energy. I can do work to it to give it energy. But look, when I do work, what am I causing it to do? And motion means it has. So there is some relationship clearly between the work I do and the object's kinetic energy. If I do work, I cause it to move, which means I cause it to gain kinetic energy. So we're going to see a little bit of this in the rest of this lesson with work and kinetic energy. Again, the units are joules. And if you don't believe me, you can do a little analysis. Kilogram times meters per second, square the meters per second. You end up getting kilogram, meters squared per second squared. But kilogram times meter per second squared times meter, this is a Newton times a meter is a joule. So that's why it is joules still, just so you know units-wise. This is squaring meters per second. Move over one of them, you get the joules. The idea, though, is that if you do work, you're going to cause motion. Or you're going to cause, if it's friction, instead of motion, you're going to cause it to do what? Instead of gaining motion, losing motion. Slowing down. Okay, slowing down. So there's an example to start. We have a couple minutes, so we'll look, and this is an easy one to start. The other ones a little bit later are a bit more difficult than this. So this problem says a 12 kilogram bowling ball moves at 3 meters per second. How fast must a bouncy ball travel? You know what a bouncy ball is, right? Super Bowls. We're going to use them in this chapter for sure. We're talking about tennis balls, golf balls, ping pong balls, bouncy balls, basketballs, soccer balls. So the bouncy ball is far smaller. Look at its mass. It's in grams. Notice that right away, not in kilograms. So it's going to be a very small mass. But we want them to have the same kinetic energy, right? So let's start by saying this. Kinetic energy object 1 equals kinetic energy object 2. Again, because of this statement right here, I've underlined in red what gave us that statement right there. Again, we need to break down the problem. For them to have the same kinetic energy, that tells you set the kinetic energies equal to each other. Then we could go ahead and use our formula for kinetic energy. 1/2 m1 v1 squared equals 1/2 m2 v2 squared. The 1/2s are on both sides. They cancel. The mass of object 1, let's call object 1 the bowling ball. The bowling ball has a velocity of 3 meters per second. The bouncy ball's mass is 4.5 grams, which is 0.0045 kilograms. And I want to solve for V2. Okay, I want to solve for V2. All my givens are above this box in area. Okay, I want to solve for V2. I can solve algebraically, I can plug in 12 times 3 squared equals 0.0045 times V2 squared. Solve for V2. V2 will become, for this problem, just so you have a number, if you're checking, 154.9. What's the point of this problem? What do I want to emphasize by doing this problem? For a bowling ball to have the same energy as a bouncy ball, look at the difference in velocities. A bowling ball is moving at 3 meters per second. That's really slow. 3 meters per second, this is 2 meters per second. That's 2 meters per second, literally. 3 meters per second is not very fast. Look at the bouncy ball. This needs to be fired like a bullet speed. Homework has not been listed yet. Here's what you need to do over the weekend. You need to read 6.1 and 6.3. 6.1 and 6.3. I will probably update the homework assignment to include the problems on the last slide. Anyway, without further ado now, let's get started. So, the work kinetic energy theorem. So the work kinetic energy theorem tells us this. Ready? Yeah. Here's what it tells us. If we do work, the energy, or the kinetic energy, will change. If we do work, the kinetic energy will change. So, and I already gave this demonstration, as I apply a force over a distance to this eraser, as I push on it, it either increases or decreases its speed, therefore changing its kinetic energy. So that's what's happening here, the word kinetic energy here. But let's derive it. Let's go through where it comes from. So when I say derive again, I mean let's show where the formula all started. And a lot of this goes back to F equals ma. A lot of the stuff that we go back to even today in AP Physics, right, Em? We talked about momentum, which is actually in a momentum, it's the derivative of that, which you're going to learn about in calculus next year. But a lot of these rules go back to F equals ma. So that concept of net force equals mass times acceleration shows up over and over. We're going to see it here. So let's start first with our definition of work. And our definition of work is work, oops, that's a W. Work equals F net times D times cosine theta. And that's our definition of work to start. And we could say work net if we want, the net work done. FD cosine theta. That's from the beginning of this section. We had FD cos theta. If I'm looking at the overall work, I need to look at the overall force acting on this object. Then we want to say to ourselves, F net. Well, that is M times A. So on the next line, let's replace F net with MA. So replacing that with MA. We are going to then look at a scenario or emphasize the fact that this is a one-dimensional problem, and we're going to look at a problem where there's only one force acting on it, and it's moving in the same direction that that force is acting on it.
Sneeze.
Miss Meyer, she has a very unique sneeze. Very loud. So the net force is to the right, the motion of the object is to the right. What does that make theta equal to? If I'm pushing it to the right and it's moving to the right, what's the angle between these two vectors? Zero. So cosine of 0. What's the cosine of 0? Just 1. So this really goes to become W net equals MAD. Okay, M-A-D, MAD. Now, you might say, all right, this is no relationship between work and kinetic energy. I don't see anything with kinetic energy yet, and I would agree with you. There is nothing to do with kinetic energy on this board so far. So let's show where the kinetic energy portion of this derivation comes from now. A times D. That expression has actually showed up already this year. Does anybody know or recall where the expression A, and I'm just rearranging the multiplication, right? Multiplication is associative, so I can group it accordingly. I can go from NA times D to M times AD, and it's the same thing. Where have we seen AD or AX before? What formula involves the product of acceleration and displacement, or acceleration and distance in this case, because it's only one dimensional in one direction? What formula?
The projectile motion is like initial velocity equals final velocity times.
You're totally on the right track, but you're not saying it right?
Yeah.
Can somebody help him out? But he's on the right track. It is definitely kinematics, projectile motion you said, but kinematics.
V squared equals VO squared plus. Okay.
Anybody? Yeah.
two.
Yep.
Delta X.
A delta X. Very good.
Yeah, 2A.
Okay? That formula over here is absolutely where AD comes into play. And D in this problem is the distance traveled, which, because this is a one-dimensional problem and this object is only being pulled to the right, D and X are the same thing. Again, D and X are the same thing. Because the problem starts here, right? I get pushed by something behind me, pushing me in this direction, and I end maybe here. That distance traveled is the exact same thing as my displacement. So X and D are identical for this problem. So in this formula, I could say V squared equals V naught squared plus 2AD. I'm going to replace delta X with D. I'll get back over here in a moment. Okay, I'll get back over to the left-hand side in a moment. If that helps you, maybe do that on yours, okay? We're doing like a side note on the right here. Now, if I look at this formula, I see AD right here. I see AD over here. So I have what scenario in play? System of equations. Very nice. And I can use what method to combine them? What method? Substitution, for sure. We rarely use elimination, you've noticed. So let's go ahead and solve for AD on the right side here. Again, let's solve for AD on the right side there. So I'm going to move V naught squared over by subtracting it. Think of this as a number. Remember, think of this as a number. And then I want to get AD by itself, so I have to get rid of the 2. So I divide by 2. So subtract the V naught squared and then divide by 2. Take that expression for AD now, as Caroline said, and substitute it in here into the formula where you see an AD in place. And what will we get as a result? What will we get here? We'll get W net. Yeah, good.
Equals m times parentheses v squared minus v0 squared over 2.
Agreed. Does anybody see where the kinetic energy comes into play now? It's like so obvious, it's not obvious. It's so obvious that it's not obvious. Good.
Wait, it's like, isn't kinetic energy formula m like 1/2 m times v squared? So
M times v squared divided by 2.
yeah.
M times v squared divided by 2. So this is definitely kinetic energy. Let's do this. Let's distribute the m to both terms on the top, and then think about this over 2 as being a 1/2. So I could rewrite this as W net equals mv squared minus mv naught squared all over 2, which is really the same thing as saying W net equals 1/2 mv squared minus 1/2 mv naught squared. And this is the final kinetic energy, and this is the initial kinetic energy. Think about this as the initial velocity, so it's the initial kinetic energy. This is the final velocity, it's the final kinetic energy. So the theorem says this. That's what it says. The net work done on an object is equal to, when I take a subtraction, what am I talking about? Subtraction means?
Like the net force.
Good, I like that idea for forces, but here, when I look at a subtraction of these two, what am I asking about? The difference between. So another word for difference is the change in kinetic energy. So the net work done on an object is equal to the change in kinetic energy. That's the whole formula right there at the bottom. And although this formula is not given on your formula sheet, you're going to notice it is not there. Okay, you're going to get W equals delta K. It's not listed anywhere on your formula sheet. Kinetic energy is listed on your formula sheet, though, and so is work done. So you can use this governing theory and apply those equations. So for example, if you were given something about the force and the distance, you could find the work done on the left side of the equation by doing FD cosine theta and putting it over here. But then on the right side, you could replace delta K with 1/2 mv squared minus 1/2 mvo squared if you know the mass and velocities. If you know, say, the initial kinetic energy and the final kinetic energy, you can place them right here, and you get the work done. So there are really 3 equations that we can use for this. Any of those work depending upon what's given. But really, you should just memorize one of them. You should not, by any means, memorize all 3 of these. This is one of those equations that you do not have to derive on a part 2. Maybe you want to write that in big letters. You could start with this on a part 2. You don't have to derive this on a part 2. Because this is a theory. This concept is called the work kinetic energy theorem. You do not have to show where this comes from, but you have to be able to use it. So if you start with what's circled here, that's good. But it's even better if you can then go to the next line, which is like this right here, and then really, which is this line right here. It just depends on what you're given. Okay? In a scenario where I'm given the initial and final kinetic energy, it makes sense to use this line right here. But if I'm given the velocities and the masses in the problem, then I'm probably going to use this line right here. Everybody see what I'm talking about right now? How these last 3 lines all matter? But depending upon the scenario, you may use one of the other, or one of the 3 differently. And the last thing to reiterate is, again, that if a problem has something to do with work, you could also replace W with f d cosine theta. And remember, that's where we started this whole thing, right back up here, right? That's where we started with f d cosine theta at the top. So if you need to replace net work with f d cosine theta, you can replace it on this side of the equation. So delta K can be replaced with this, or it can be replaced with this, either of the two lines above it. W net can be replaced with FD cosine theta. So depending upon the scenario, we may or may not replace certain parameters in this theorem. Jack, you had a question?
If it was in like 2 dimensions,
Mhm.
would you just multiply cosine theta to the whole thing, or how would that work?
So no, unfortunately, the way this theorem is going to work is only going to be a one-dimensional theorem. The kinetic energy that you're looking at for this has to do with kinetic energy when you're only moving left to right. So maybe put a nice star at the top here and say to yourselves, this theorem only applies when there's no vertical motion. So although I started by saying it's a one-dimensional problem, specifically one-dimensional along the horizon or horizontally, Jack. If it moves vertically, we're going to talk about section 6.4 in a little bit, where that involves potential energy. So I would only use this formula when I'm looking at an object that is moving along a horizontal surface, not any vertical motion. Yes?
I'm confused. If you plug something into like, say like W net equals delta K, how would that like help you find something?
Give me 2 seconds and we're going to get to an exact example on that actually. So we're going to show why we might want to plug something in here. So maybe I'm asking you, Julia, to find the overall force felt, and you have to solve for F. You know D, you know cosine theta, you know M, you know V, so you can plug that expression in over here and then solve for one of these unknowns in the formula. But it depends on the problem, so there's no like one answer right now. That's the hard part with physics, right? There's no one answer to your question. Depending upon the scenario, we may have to replace W with this, or maybe not. Maybe the problem will give us the total work done, 17 joules, and we just put a 17 in here, and now we don't have to replace it anymore. So we'll see what we're given in the problem, maybe by listing our givens to help us to see which will go. Okay? So let's see what we're going to do with this, or with this idea. So the first example says the following. How much work is required to accelerate an aircraft, and this is the approximate mass of an aircraft, from 4 meters per second to 70 meters per second. And both of those speeds are reasonable as well. 70 meters per second is like 200 miles an hour, which is what aircrafts need to lift off. So we're talking about the work done to accelerate an aircraft from where it's just barely rolling to where it's about to lift off. So we're given in this problem velocity initially, velocity upon liftoff, and we're given mass. Velocity upon liftoff, velocity initially, and mass. So if I start this problem, I could start it by saying, let me list my givens. And let me list what I'm looking for. So that's all my info right there. It says how much work is required, right? How much work, which is capital W. It's not the force. It's not the force being applied. If it said what force must be applied so that this object lifts off after 100 meters, then we'd be given D, and we'd be want to solve for F in that problem. But for now, it says how much work is required to accelerate it. So we can start this problem with the work kinetic energy theorem because we have a change in velocity occurring and we're looking at work done. A change in velocity indicates mentally that there's a change in kinetic energy. A change in velocity means a change in kinetic energy. So if you need to underline that, do it. Underline 4 to 70. And just write yourself a note that this is considered a change in velocity. And if there's a change in velocity, there must be a change in kinetic energy. So we start with the work kinetic energy theorem. Since we're looking for work, I could leave W alone. I could do final minus initial. And final kinetic energy is this. And initial kinetic energy is this. So I'm literally going backwards a couple steps in my derivation to come up with the third line we have here on the right. I'm just replacing delta K with final minus initial, and then K final is 1/2 mv squared, and K initial is 1/2 mv naught squared to stand for initial velocity. And at this point it becomes a plug and chug. go right through the problem. Plug in the 10,000 for mass, the 4 for initial velocity, the 70 for final velocity, and I can see what the change in kinetic energy is. And by all means, factor out a 1/2, factor out a 10,000, but don't drop it off. If you're going to factor it out if you want to, some of you like to just make things simpler, and I agree. 1/2 m is in both terms. You can factor 1/2 m into the front, and then add v squared minus v naught squared, and it'll still come out to be the same answer. Okay? So what do we end up getting for this problem? How much work is done on the aircraft? Why do I say work done on the aircraft? Not by the aircraft, on the aircraft. What do you think? Yeah.
There are like forces acting on it.
Yeah, what force? What force is propelling this aircraft forward?
Thrust.
Thrust. Very good. Well done. The force is called thrust. That's what what are they called? Turbines. Push air out the back, and Newton's third law says a force pushing this way causes the aircraft to accelerate forward, equal and opposite. So the force of thrust pushing back is what propels the airplane forward. So really, there's a force of thrust acting on the airplane, What else allows the airplane to move along the ground and propel it forward along the ground? Yeah, specifically, what kind of friction? Rolling friction, yeah. The wheels, right? As the airplane starts to move, it's got to have friction between the wheels and the actual ground in order to propel it up to the speed it needs to get to. So this is the work done on the aircraft. I'm getting a large number, right? 2.44 times 10 to the 7. And that answer is in joules. If I wanted to write it with the prefixes that we know, anybody remember a prefix in this area? Anyone remember prefixes on this order? Like, what was 10 to the 6? Anybody remember what that prefix was? 10 to the 6?
That's million.
Good, million, but what does it actually stand for?
Oh, it is like hexa.
It's not M. M stands for not million, believe it or not, though, yeah. It is million, though, you're right. But it's not M for million. It's M for mega. Mega. Like, remember, think about computers. Kilobytes, megabytes, gigabytes, terabytes. Remember I went through this in like second, third day of the year? So if I wanted to, I could say, well, this is really just 24.4 times 10 to the 6 joules, which is really 24.4 megajoules. Capital M stands for mega as a prefix. Like kilometers is lowercase k, or lowercase c is centimeters. Capital M is mega, and mega stands for 10 to the 6. So I change this, I move this over one spot, which makes it 24.4, so I reduce that by 1 to compensate for moving it over. And then I saw 10 to the 6, which is really mega. Now, I don't care which way you answer it for this problem, okay? This is fine right here, what I've circled in red. It's totally fine. Follow-up question. 2 follow-up questions for you. Follow-up question number 1. Could we have done this another way? Could we have found the work done another way without using the work kinetic energy theorem? The answer is yes, so I guess I should say, can you tell me or can you see another way to solve this problem without the work kinetic energy theorem? Yeah, okay.
Could you use the v squared equals v 0 squared plus 2a delta x?
How come?
Because the AD is the same as AX.
You're on the right track. She's seeing a connection there with the AD and the AX portion. It's definitely all on the right track, yep. I mean more than that though, you know. You give me an idea because it was the derivation, but what else could I have done? Start with what's the definition of work? Before we get to kinetic energy, work was defined earlier as F times D times cosine theta, right? So if I'm going to use F times D times cosine theta, what would I need? I would need the distance traveled, and I would need the force. The theta is going to be 0 because it's going this way. The force is pushing it this way, so it's got to be 0 degrees. So I could have started this problem with work equals force times distance. And since we're looking for work, we could have gotten force with mass times acceleration. And acceleration is my change in velocity. Change in velocity. Oh, But what don't we have? We don't have distance and time. Because by definition, acceleration again, is change in velocity with respect to time. So we would need to do something in this problem. Vin, what are you thinking? I saw your hand go up.
V squared equals v initial squared, even though it's 2a times delta x. And say delta x equals d. Then we solve for a, it's d delta x, and delta x equals
Yeah, so that's exactly right, Vin. Very good. So what Vin is saying is, hey, you know what? We could have used the same formula earlier, like Caroline said. V squared equals v naught squared plus 2a d in this problem because the distance and the displacement are the same. We could solve this equation for a, plug that in for a. What I'm getting at is we could do it this way. But look what it takes. It takes a couple equations and a little bit of work, right? So the work kinetic energy theorem saves us a good amount of time. I don't want to have to always go back to kinematics. I like energy methods. And I talked about AP physics. Energy methods are easier to solve. Whenever you could use energy instead of old school kinematics, it's less work. Less work. Work? Yeah. Not physics work, but physical work, right? So it is a lot easier to use the work kinetic energy theorem instead of this entire piece over here, solving for A, plugging in for A, and then going ahead and evaluating. That's my first follow-up question. My second follow-up question is as follows. If can I say that? Yeah, I could. Okay. If the distance, or if the length of the runway, so that was the second one, if the length of the runway is a given value, how can we determine the thrust force acting on the, what do you call this? Aircraft. George.
You get the distance, then you can find the acceleration, and then you can do F equals ma.
If we had the distance, then we could find the acceleration and use F equals ma. Where is F equals ma going to play a role?
And finding the force.
If we had the distance, we could find the acceleration. Yeah, I like that. Yeah. So that's kinematics method. So George said if we want to figure out the force, he said if we have the distance can lead us to finding the acceleration. And once we have the acceleration, we could do m times a to get the actual force. That's what you're saying? Yeah, I like that approach. There's another approach, though, and that's kinematics. How about with energy and with work? With energy and with work now. This is where it gets a little bit tricky. This number is the work done, right? Acting on the object right here. This is the work done acting on the object right there. But what's the definition of work again? What did we say the definition of work is? F times D. So if you had D, you don't even need to get A, George. Right? This works. What you're saying works, George. But this is a longer method, right? It takes longer to do all that work. So let's go back to now thinking, if we have the distance now, we have it, what can we do? Yeah.
Wait, but I thought you said it's the work by aircraft.
So this is the work done on the aircraft, and the thrust force is acting on the aircraft. So the turbines push back, and the thrust force pushes back on the airplane. Do you see what I'm saying? I know it's a little bit weird, and it's really the rolling friction that propels it forward, actually. So if there was no friction on the floor and you propel backward, the object itself will just start to slide forward slightly. With the wheels there, it helps propel it forward. There's a thing, what is it called? These things they ride on like marshes, where there's like marshland, a lot of marshland, and they got these big like fans in the back of them. Anyone ever see these things before? They're like boats, but they've got these giant fans in the very back.
Yeah.
You've seen, what's the movie? Waterboy, the Waterboy with Adam Sandler. He rides in one of these at some point, I think. Anyway, if you have something propelling backward, it automatically pushes you forward. This is a terrible example. I'm going to give an example that's really weird. But imagine you're running and you like started farting. I know it's a terrible example because it's gross, but think about it logically, right? I know. You're running, right? If you farted like really hard, I mean, and I know this is crazy, but that propulsion backward will propel you forward. Literally, that's how a rocket works, right? I know. Rockets, right? They burn fuel and they push gas out the back of the rocket, which propels the rocket upward. It's no different than a fart when you think about it, you know? Now, again, not the greatest example, but you might remember that. So, anyway, my point is, the force applied is on the airplane because it pushes back against the air with the thrust force of the turbines, and that propels the plane forward. So, the question was, how could we figure out the force? And what we could do is we could use this value, and we could say work equals FD cosine theta. And since we have the work is 2.44 times 10 to the 7 joules. And we're looking for the force. If I gave you the distance, and we know that this is the cosine of 0 degrees, which becomes 1, we could solve for F. So I want to point this out real quick again, that in these problems, they might be a two-step problem. Part A has you find the overall work done using the work kinetic energy theorem. And then part B, I might say, well, you know what? That work, that energy right here is happening for a certain distance. I'll give you that number. That's why I'm putting a number sign here. It's not given in this problem. But you're given, say, it's 8 meters. Well, that's going to not make sense at all, right? Let's think about an airplane lifting off. It's more like, what? How long is a runway on average? What do you think? Let's use our number signs. It's got to be quite long, right, for an airplane to take off on it? So it's probably like 2-3 football fields. So we're talking like probably a couple hundred meters. So maybe the distance traveled is like 250 meters. Divide this number by 250 and you'll get the force of the turbines that the plane is propelling forward with. My point is, again, that the work kinetic energy theorem can give us an answer for joules, but then because we know what the work done is equal to this, we could also find the force. Or what if I gave you the force? If I gave you the force of the turbines, what could you then determine or solve for? The distance of the runway. So if I said to you, well, you know what, it turns out that the force of the turbines is 10,000 newtons, determine the length of the runway that's needed. Well, then you would solve this for D if I gave you the force of 10,000. So these would be switched. You'd have this number and you'd be solving for D. I want to point out all the ways that you could use this theorem and how you could adapt while using the theorem.
Is the force you're finding really the net force though?
It is, absolutely. This is the net force acting on the object. So that force is like the difference between the turbines pushing you forward and the air resistance pushing back against you. It would be the net force. So the statement would have to say the net force, or it could say the thrust force of the turbines pushing you forward is this value. Assume there's no air resistance, and then that would be the net force by default. Okay? So the work kinetic energy theorem is very useful. Let's see a second example of this. What do we end up getting for this problem? Whoops. Where we may earlier take a look at substituting FD cosine theta. You're on a wood floor. Oh, by the way, this is one of my favorite ones. So this is an extra credit opportunity for this quarter. So, extra credit, extra credit. I know a lot of you took advantage last quarter. Here's another great one. For those who are out today, let them know about this extra credit, or they'll hear about it in the video when they listen. So here's your extra credit for you. There's a movie. I don't want you to recreate the scene like it's recreated in the movie at all. Because there's a movie called Risky Business with Tom Cruise. You know about this? Okay. Tom Cruise. Yeah. It's always Tom Cruise, right?
Where he slides in, he has a button-down shirt on.
He's wearing like boxer shorts and a button-down shirt. And he comes in with a guitar, I think, right? It's a guitar. He slides into the room with a guitar in his hand. I think he's got the guitar. Does he?
Do that or like air guitar?
Something, yeah, maybe
It's an
air
air guitar.
Anyway, he's got socks on. He's got shorts on. Please be fully clothed. I say that now, be fully clothed. He's got shorts on. He's got a t-shirt or a button-down and like socks. The key, he's got socks on. So he comes into the room and he like slides. I can't do it here because there's too much friction. But he slides across the floor and it's like a wooden floor. So this is like, I don't know why this is a thing. I thought of it in the past, and then I saw this movie, or I saw this clip in the movie, and then I actually watched a video the other day, a TED Talk on friction, which I just posted on your news forum today. And in the friction talk, this woman, she studies friction for a living. It's called a tobologist or something like that. I forget the phrase. She literally studies friction for a living. Anyway, in that scene, she goes, you know, in the TED Talk, she goes, you know that feeling when you put a new pair of socks on and slide across the floor? And I was just like blown. I'm like, this is what I talk about every year. Because it is very, very low friction. So anyway, your extra credit is put a pair of socks on that have very low friction. So maybe like, you know those socks that are really soft in the wintertime that sometimes you wear? That are like really fuzzy sock kind of things? Yeah, they're like the footsie socks, but without the grips on the bottom. And what I want you to do is this, and it's tough. It's not an easy extra credit for sure. I want you to videotape yourself, and I want to get you, so you're going to be like running up, and then I want you to kind of like do something like that and slide across the room. Now, I'm going to introduce you to a program in about 2 days, so you'll be able to use this program if you want, that you can actually find your velocity along the way. It's called Vernier Video Physics or something like that. We're going to get into it with a lab soon. And you can actually, did we use it already this year?
We have.
We did? I forget if we used it here or if it was in math freshman year. So with Video Vernier, you both, okay. So record with Video Vernier yourself coming in and sliding across the room. You need to figure out what your initial velocity is though. That's the key to the whole problem. I want you to calculate the coefficient of friction on the floor between your socks and the floor. The actual value. We're going to get a value here, or we're going to find the distance. Yeah, how far will you move? Given the coefficient in this problem. But I want you guys to measure the distance that you slide for. You could have a tape measure. You could have a ruler, a meter stick, whatever you want to use. Measure the distance you slide for. Know your initial velocity you come into the picture with. And then what is your final velocity going to be? 0, because you're going to stop, okay? But you need to be in the frame of the picture from beginning, from when you do this, to when you're like, all the way over here, and now I can't do it on this floor. So the picture needs to capture you like that entire time. So I need to see the entire frame so I can see your initial velocity, I can see that it stops, you can measure the distance, and your goal is going to be calculate mu for this problem. A good opportunity for 3 points on your next test if done really well. If done all right, maybe 2. If done just all right, maybe 1 then. Yeah.
Do you just submit like the work, or do you submit?
Same as last time.
Like
It should be
video?
a video for sure. And then with that video, either it could be a voiceover of you explaining it with the math involved, or if you want to, it could be a video and a physical written submission going through all the math and all the work for it. That's fine as well. I like it all to be in one video, but it doesn't really have to happen that way. So it's up to you to decide. But I want a video, an explanation, and mathematical support. Those things. If you just have a video and you explain it, you're not going to get the full 3 points. So you can do that still if you run out of time, but I'd recommend going through the whole problem. So you're on a wood floor, right? You slide around, you put on a pair of socks, you run and start to slide with an initial speed of 2 meters per second. How far will you move if the coefficient of kinetic friction between your socks and the floor is 0.1? So let's start by listing our givens. Coefficient of kinetic friction, mu k, that's given to start, 0.1. You run and start to slide. I was nice. I said with an initial speed. So what is that referring to? V0. What is your final velocity? Why? Because you're eventually stopping. Good. How far will you move is meaning you're going to stop eventually, right? Or else, how far would you move? The answer would be infinite if you didn't stop eventually. So we're looking for how far. What do you think? Distance. I agree. Now, based on the givens in this problem, we clearly are going to be using some part of the work portion of the work kinetic energy theorem. Because the work portion is FD cosine theta. And the delta K is 1/2 mv squared minus 1/2 mvo squared. So we're going to use part of each side of the equation because we have to get D. We've got initial and final velocities here. So we're probably going to also use the kinetic energy portion of the equation. What's not given in this problem at all? That we probably do need or should need or have needed in the past, but maybe we don't need it right now. What variable is that? Mass. Mass is not given. So what do you think will happen if mass is not given, yet it's in the formula somewhere? What do you think, Seb? Yeah, mass has got to drop off somewhere. So let's start with our work kinetic energy theorem here. So we've got the work done equals the change in kinetic energy. Right, that's the whole theorem. And then from there, we keep going. What do you suggest I do next, Caroline?
Choose the right
the formula to W net equals MAD?
To MAD, we could go to that, but that's going back to our derivation. I don't want to go back to our derivation from earlier. I'm gonna stray away from that derivation from earlier, if that's right. Christina?
Replace W with FD cosine theta.
I'll start with that. Can you tell me why you're using FD cosine theta in this problem, while the last problem, Christina, we did not use that, right? How come we're using it here?
Because you're given D and then cosine theta drops off, so it's defined the net force.
Yeah, so really we're looking for D, so there's going to be something with F here, there's going to be something with cosine theta, so we're going to have to utilize this formula to find D as the key. All right, I agree with that. Now here's a question for you. What is doing the work? What is doing the work on this person? What force? Remember, forces are what do work. Forces do work. Forces applied over a given distance do work. Then, frictional force. So let's write that, please. Let's call that FF, because it is absolutely the frictional force. I would agree with Ben. Again, think about it. You're sliding and then you stop. The only thing that can happen there is some sort of frictional losses. Okay? How about the right-hand side of the equation? What does that become? Change in kinetic energy. What could I can write K minus K initial. That's fine, but let me jump to the next line. What could I write on the right side of the equation? What are my formula for kinetic energy? What's my formula?
Oh, are you talking about the 1/2 mv squared minus 1/2 mv naught squared?
Very good, sir. Well done. 1/2 mv squared minus 1/2 mv naught squared. So what we're noticing right away is that we've got all of our parts of this equation being used now. We're using the kinetic energy side and the work side both. So this is back to your question, Julia, of when are we going to know? When do we replace work with its definition? When do we not? The last problem, we didn't do this because we were looking for work, so we only replaced this side and got an answer. But now we're looking for distance, so we have to replace. What is the force of friction by definition? What is the force of friction by definition? Justin. Fn times mu. Let's replace that. And what could I put a 0 through? What could I put a 0 through at this point?
The half mv squared.
The what?
The half mv squared.
Yes, right here. That is 0. How come? How come? Somebody else. Why can we put a 0 through that?
Final velocity is 0.
Final velocity is 0. Sure, the mass is not 0, but I don't care. 0 times anything is 0. Okay? So that makes that convenient. This is still a negative here. Don't forget this negative right there. Right? That's going to carry down in a moment. 0 minus something is negative. All right, next. Next. I still haven't canceled mass, right? So something's got to give. We got to have some sort of substitution to get rid of mass. What do you think, George?
Oh, you're going to replace Fn with mg.
How come Fn is equal to mg, George?
Just because there's no change in y. Height.
There's no... Be
Like,
more careful
delta
then.
y.
Okay. Can somebody else help me out with them?
Sorry, MAY. Like AY.
I like that. There's no AY, so therefore there's no what acting in the y direction? No net force. There's no extra force acting in the y direction. If this were a scenario where an object's being pulled at an angle, remember, partially it acts up and partially it acts to the right, which changes Fn. But whenever there's a balance vertically between Fn acts up and Fg acts down, we can automatically replace Fn with Fg. But Fg is really just mg from earlier in the year. Now what happens, obviously? Now the masses cancel out. And this problem simplifies a bit. Mu k d, there's a g in there, sorry. Mu k g d cos theta equals negative 1/2 v naught squared. I'm dropping my masses off. How am I going to account for this negative here? Because if I see a negative here, it seems like when I solve for d, I'm going to get a negative answer. Right? If I solve this for d, mu k, g, cosine theta, divide these all over here, it looks like I'm going to get a negative answer. How is that negative going to be taken into account? What do you think, Christina?
Since the net force is friction and it's going against the motion, then the work should be negative.
then the work done is negative. So where does the negative come into play a role? You're right. Christina's totally right. Friction is doing work, so the work done should be negative, but I don't see a negative here, right? Christina, it's missing. There's no negative. So where is the negative coming in?
Negative 9.8 for gravity.
No, good try though. Remember, this G is not negative. This is just 9.8.
Is it cosine 180?
Think about it. If I'm moving this way, the friction acts this way, what's the angle? The angle is 180. Whenever it's the work done by friction, the angle is 180, right? So in reality, what does this problem become actually? Well, this becomes the cosine of 180, which is really equal to negative 1. So the negative on both sides of the equation will cancel and leave me with mu k GD equals 1/2 V naught squared. Again, cosine 180 is negative 1. The negative drop off on both sides. I'm left with this line. And then I can solve for D. Okay, that's what D will become if I solve for it. I'm putting it over 2, same thing as 1/2, right? 1/2 of something, same thing divided by 2. I've got V squared over 2, and then when I move the mu k and the G down, it goes down below here, which come down below to the denominator. Okay, that's our answer for D. So what are you guys going to have to do with the extra credit? Really not much more than this, right? With the extra credit, you just have to go here, right? Up to there, where the asterisk is, and then solve for what? Yeah, that's it. That's all the extra credit is. And I want you to recreate it. I want you to step me through the process, explain the reasoning behind it. But it's literally the same problem as this, except where the asterisk is, you're going to solve that for mu. So this extra credit is more about, I want you guys to take data. I want you to use video veneer, get good data, get reasonable data, and your answer itself should be reasonable. So if you get a mu and it says like 7.8, probably not right. Mu is traditionally between like 0 and 1, sometimes more than 1, but not much more. So if your mu value comes out to be a negative number, something's wrong. If you get a number, again, like a large number, it's probably not reasonable. So number sense when calculating here, okay, number sense. Anyway, that's the answer for D. What does D become if I solve? What do we end up getting, approximately?
2.04.
Yeah. Okay, this is around 2. I think it's 2.04. Is that what it is, Jack? Okay, around 2 meters. That's the distance this object would travel. Again, I'm going to point something out. I'm not going to go through the whole thing, but I'm going to say it. This problem could also have been solved with forces and kinematics. You could have used F equals ma. You could use all that kind of stuff to find the distance traveled. By all means, you can do that. I'm trying to show you that one formula can do everything for you now. Okay, so it's one formula you start with, and then you're just making a lot of substitutions along the way, as opposed to F equals ma, and then your kinematic equations from much earlier in the year. Okay, so I would recommend using energy whenever possible. Use energy whenever possible. Okay, I think that's the last part. I want to stop there for today on this one. I want to start 6-4, which I'm going to do. Again, this is why I said, please space out your homework. It's not a difficult homework, but it's lengthy homework. The first 5 and the next 4 on the next page or 5, those are all conceptual problems. The mathematical ones are from 164 to 165. So if it were me, I'd probably do all the conceptual maybe tonight, and the mathematical tomorrow, or vice versa. But I would not wait till tomorrow night to do all this homework. Okay?